Good evening, ladies and gentlemen. Welcome to the short prize lecture in Mathematical Sciences 2020 by Professor Alexander Berninsen and Professor David Kastang, the Short Laureate in Mathematical Sciences 2020. May I first invite Professor He Xuhua from the Department of Mathematics, our moderator today, to introduce the laureates. Professor He, please.
Good evening, everybody. The first speaker of today is Professor Alexander Berninsen. Professor Alexander Berninsen was born in 1957 in Moscow, Russia. He's currently the David and Mary Winter Green University Professor at the University of Chicago, USA. He obtained his PhD in 1988 from the Landau Institute of Theoretical Physics. He was a researcher at the Landau Institute from 1987 to 1993. And a professor of mathematics at MIT from 1988 to 1998, before he moved to Chicago. In 1999, Berninsen was awarded the Ostrowski Prize. In 2017, he was elected to the National Academy of Science. In 2018, he was awarded the Wolf Prize. And the title of Professor Berninsen's lecture today is Zeta Values and Motific Periods.
The lecture is about zeta values and motific periods, and this is a part of mathematics that I was very interested quite a while ago, but it's still being mostly conjectural. It still holds to be interesting today. Well, let me start with a Riemann zeta function. It is defined as this product, and it's easy to see that the product converges absolutely for the real part of S more than 1. And this is probably one of the most mysterious and functions in all mathematics. Well, one knows that it extends holomorphically to the whole complex plane except simple pole at 1. And it also satisfies a wonderful property that if you consider its value at positive even integer, then it equals pi to the power of this very integer times some rational number. The basic question is, well, to understand what is the meaning of zeta values of zeta function at an arbitrary integer? Actually, this zeta function is a particular case of more general zeta functions that I would be interested in, and the zeta functions of algebraic varieties over integers. So let me say how you define it. So suppose that you have x that x be an algebraic variety over integers, and well, if x is affine, this means just that we have a system of polynomial equations of n variables. So f alpha are polynomials with integral coefficients, and x is a subset. Well, x lives in the coordinate vector space and given by this system of equations. That's what are affine algebraic varieties or schemes over Z. And to such x, we can assign its zeta function, which is defined as follows. So again, I assume for a moment that, well, for the sake of simplicity, that x is affine. So we have a huge ring of functions. And what we do, we consider the product of, we consider all possible maximal ideals inside of this ring of functions. And we consider the product of 1 minus the order of the quotient. Then if the ideal is maximal, then the quotient is finite, power minus s, and then again minus 1. And if O of x is just the ring of integers, then this will be exactly the Riemann Zeta. And this is invariant of, well, of an algebraic variety. And again, it's an extremely interesting invariant. And the same question is, what is the meaning of the values of zeta at integers, say at positive integers? So same question. It appears that this question has to do with topology. Namely, if we have such a variety, we can consider its complex points, its solution of this system of equations with when x are complex numbers. And this is some subvariety in vector and dimensional vector space over complex numbers, and you can consider its topology. And it appears that zeta function has to do very much with this topology. So let me explain the reason. Well, consider, this in the zeta function there were these products where occur the quotients modulo maximal ideals, and each of them has some characteristics, some prime number p. And let's fix for the moment a prime number p, and let's consider the ring of, again, I assume that my varieties are fine. Let's consider the ring of functions modulo p. And an absolutely remarkable fact in which has to do with rings in finite characteristic is that such a ring has a canonical symmetry which calls Frobenius. And the symmetry sends every element of a ring in its p power. Since we live in finite characteristic, this thing sends the sum of functions to the sum, and it's a ring endomorphism. And to see the connection with topology, let's assume for a moment that this Frobenius endomorphism leads to an endomorphism. Assume, and that happens very rarely, that it leads to an endomorphism of ring of x, which I call Frobenius tilde. And then certainly it acts, same thing, acts on the set of complex solution on x of c. And we can rewrite the part of zeta functions of those products which live in characteristic p. We can rewrite it as using fixed points of this endomorphism of this topological space. Well, let me write a formula. Let's consider x modulo p. And this is the product of all factors in zeta function which looks as 1 minus p power a minus as, and that's minus 1, so p power a equals the order of modulus is maximal ideal. So we consider the part of those, and then remarkably you can rewrite the thing as a product of, with respect to fixed points of this Frobenius tilde, and namely we should consider not only fixed points but orbits of finite length, and this will be a product of 1 minus p power a s power minus 1, where a, with respect to all length a, product with respect to all a, and with respect to all length a orbits of Frobenius tilde acting on x of c. And then, the moment we have such an expression, we can rewrite it well, using elementary algebraic topology, namely Lefschetz fixed point formula, and then it will be given as just a very short rational function. Namely, it will be the product of characteristic polynomials of Frobenius time tilde times p power minus s acting on cohomology of x, maybe with compact support, with rational coefficients, and then every determinant is some polynomial, and then it should be taken power minus I plus 1. Okay, now we have as many cohomology groups as dimension of x as well as real manifold. So we have this rational function, and again this observation, well, certainly it comes very rare, in a very rare situations that you could leave Frobenius to endomorphism of O of x, but something which is called Weyl conjectures tells that, well, though it's very rare, but still is a situation for general zeta functions that this sort of a formula holds. Well, it should be understood in some proper way, but still it is true. So in particular, this part of zeta function is a rational function of p power minus s. So let me just state it here. So same is true without assumption of existence of Frobenius tilde. Well, I'm cheating here. Something should be explained, but it would take too much time. But just you should assume that something similar holds. That it's always that this zeta of x mod p is a rational function which has to do with topology of the manifold of complex points of x. Well, I should say that Weyl conjectures were just the leading force for development of algebraic geometry by Grothendieck school, and it was a great success of this school, which is connected with the names of Grothendieck and Deligne, that they were actually proved. But what follows from this is that if you write zeta x of s, so it's product with respect to all p prime p of this zeta x mod p of s, Well, that somehow it has to do with topology of complex points. You should understand that it's very strange for, well, zeta function itself, it comes as we take x and we basically polarize in all its points over finite field. And topology is something very different. It has to do with continuity. But still this holds. And let me try to explain now how, well, conjectures about the values of zeta function at integer. Maybe before explaining the conjectures, one could ask that certainly here what is a bit unpleasant is that we deal with x over c and not of x as an abstract algebraic variety. And the reason for this is that that you may ask if you can develop some algebraic topology of algebraic varieties that can be just used directly without assuming lifting of Frobenius and so on. Well, and it was done, and this development is called maybe Motific topology of abstract algebraic varieties. And its development mostly has to do with names of Vygotsky and Morel. It was achievement of the end of 90s. And it is, well, there is some very different to classical topology to develop algebraic topology of abstract algebraic varieties, and in particular to define their cohomology groups. And they're called Motific cohomology groups. So I need it just for x. And they depend on two integers. One is just the number of cohomology group, and the second for, well, it's called Tate twist, and it has to do with some sort of natural local systems that exist for in this world. Well, you can maybe just for imagining the picture of x in this abstract homotopy theory looks approximately like this, that it is fibered with fibers approximately equal to x of c over some base, very complicated, and the base has to do just with the point, the spectrum of z, and it still has homological dimension 1, so that's the picture. So in this theory, somehow you could visualize yourself an algebraic variety as something like its complex points, but with extra one dimension added. Very complicated dimension. Well, now the story becomes, it also has some analytic aspect, which was developed actually earlier than this abstract theory, and it has to do with Hodge theory. And let me try to find a place. Oops. Well, this was, well, Hodge homotopy theory, maybe. It has to do with complex algebraic varieties. Well, maybe I should say y over complex numbers. And formally it looks pretty similar to Motific story, except that it is only that it is a real picture. You cannot put here rational numbers, but only real numbers. So it is, the nice feature is that that the image of a point is not here. It's also a fibration, so from the point of view of Hodge theory and algebraic variety, again, is a fibration over with fibers, usual topology. It's topological space, but the base now is actually a circle, just a single circle. In a sense, poetically, it's similar to what happened in theoretical physics long ago, something which is called Kaluza-Klein model, where people tried to consider simultaneously gravitation and electromagnetic theory, and they arrived that you could do it if you add extra dimension, one small circle to our world, so it becomes not 4-dimensional but 5-dimensional. And here it comes the same, that in Hodge theory, in arithmetic, you add one extra dimension. Let me just to see a flavor of this, maybe I should say one simple example. It is example when y is a curve, complex curve. So from the point of view of usual topology, it's a surface, Riemann surface, and it's fibered over this Hodge circle. So it's something 3-dimensional, and a point of our complex variety, it corresponds to, now it becomes a circle in this 3-dimensional thing. And you know that if you have two different circles on something 3-dimensional, you can, you can compute something which is called their link index. And in usual topology, it is an integer. And here it is just a real number. And that's a very remarkable real number, namely it is a value of the green function of a surface on this initial pair of points. So that is just feeling how strange and beautiful this topology is. Now I can come to a sort of a unification of these two things, and the fact is that this Motific cohomology groups, they map into Hodge cohomology groups. Oh, well, I did not say, but certainly it's not only Hodge name should be put here, but mostly the name of Deligne, who invented something which is called mixed Hodge structure, which has to do with the story. Well, now the main thing is that you have a map from to the corresponding Hodge cohomology groups. And this is called, X over C now. And this map is called, Motific periods, or in another terminology, it's called regulator. Now, the remarkable thing is that the thing can be computed very easily. Well, it's always not a difficult invariant, but if B is larger than the dimension of X, then this is just cohomology of X with dimension 1 less. A minus 1. So 1 comes because you have this base circle. And therefore here you have, you have a natural rational structure, so you can consider cohomology with Q coefficients. And, now I can stand the conjecture about the value of the zeta functions. And the conjecture says that first is that for again, there is conjecture for general B, but let me consider just the situation. That this map also provides a different, provides a Q structure here. So that this is an embedding of rational vector space, so that which provides, well, embedding as a Q lattice here. So it provides different Q structure. And therefore, you can compare it with the Q structure which comes, because here you have H A minus 1, X of C, Q. Well, and now the conjectures about the value of zeta, it just asserts that up to a ration, whenever you have two rational structures on a real vector space, you can consider, you get a real number defined up to multiplication by rational number. You take any base here, any base here, and you compute the determinant of the corresponding transition matrix. So relative volume of two rational lattices. And the conjecture is that if you take product of all the things, so we consider the relative determinant of this thing and this, so that of Motific just and this will be a real number, and then you should take the product of the things. Here will stand HA minus 1 with respect to product of those that power minus 1 power A, probably A. And this will be exactly the value of zeta function at x at B times rational number. It's a strange conjecture, and the only situation where it's really known, it is a case of when our x has dimension 0, that it is a ring of integers in, functions are a ring of integers in a number field. But still there are, outside there are computations in some particular cases, in particular for modular curves, which support this conjecture. But it's mostly philosophical. But still it yields much of further developments in the theory, and well, at least I like this, the things, and I'm happy to present it to you.
Okay, so we first thank Professor Berninsen for the wonderful talk on the zeta values. The next speaker is Professor David Kastang. Professor David Kastang was born in 1946 in Moscow, Russia, and is currently Professor of Mathematics at Hebrew University of Jerusalem, Israel. He received a diploma in 1967 and earned his PhD under Alexander Kirillov in 1969 from Moscow State University. After working at Moscow State University as a researcher from 1969 to 1975, he immigrated to USA to take up a position at Harvard University, where he was successfully a visiting professor from 1975 to 1977, and then professor from 1977 to 2002, and professor emeritus of mathematics since 2002. He then immigrated to Israel and has been a professor at Hebrew University of Jerusalem since 2002. He is a member of the U.S. National Academy of Sciences and the American Academy of Arts and Sciences. So today he will talk about symmetry through representation theorem.
I'll talk about symmetries through representation theorem. I had the privilege to study for many years under the tutelage of a great mathematician, Israel Gelfand, whose seminars covered and brought together almost all the areas of mathematics. From Gelfand, I learned to look for unsuspected connections between different and a priori unrelated areas. I will present some of my works on apparent and hidden symmetries. We see immediately that a ball is invariant on rotation, but often the symmetry is hidden. Representation theory is a tool to express and to enjoy hidden symmetries. Theory of representation brings together many different aspects of mathematics. In addition to group theory, it brings together both functional analysis, topology, algebraic geometry, category theory, even mathematical logic. In the 50s, Adler Selberg originated the study of discrete subgroups of real semi-simple groups of finite covolume, such as SLNZ inside of SLNR. He was interested both in uncovering properties of these discrete groups and the understanding of automorphic representation of the natural representation G on Hilbert spaces. It is known that while from almost all subgroups gamma of SL to R, the quotient gamma mod commutator is infinite, the quotients gamma mod commutator are finite for congruent subgroup gamma in SLNZ, for n bigger than 2. But the question about the finiteness of a quotient for arbitrarily large discrete subgroups of G and R was completely open. I observed that for a proof of finiteness of these quotients, it is sufficient to show that a group gamma has property T. That is, that the trivial representation of gamma is isolated in the topological space of reducible unity representation of G. It was not difficult then to see the groups SLNR and many other groups have the property T. I have also proved that any group with property T is finitely generated. After the appearance in mid-60s of Langland's conjecture on the existence of close relation between n-dimensional representation of a Galois group and automorphic representation of a group G and R, the study of representation of co-reductive groups, such as GL and QP, came to forefront. The first part of the remarkable book of J.K. Langlands contains analysis of reducible representations of the group GL2F for local fields. In our paper with Gilfand, we extended the analysis to GLNF for n bigger 2. In particular, we defined the notion of the gamma function, which is central in the theory of automorphic representations. Let G be algebraic split reductive group. For any locally compact field, the group of F points is a locally compact group, and one may consider this space of irreducible representation. Israel Gelfand and Harishchandra observed that the structure of representation for different fields enjoy a lot of similarities. In particular, an understanding of a set of irreducible representation from finite fields contained hints helping for guessing a description of topological spaces for local fields and the parameterization of automorphic forms. In a remarkable paper of 1955, Green parameterized the reducible representation of GLNFQ for group GLNFQ and computed characters of this representation. He found that both the parameterization of reducible representation formulas for characters are uniform. To appreciate these formulas, one should remember that unipotent conjugacy classes are parameterized with partitions of n. Green found that, first of all, the subset of generic reducible representation of group GLNFQ is naturally the disjoint union of subsets parameterized by conjugacy classes of a Weyl group. And he found the characters of regular generic representation of regular semi-simple elements can be easily computed. And the most interesting found for any partition lambda, and there exists a graded representation sigma of lambda of Weyl group W, such the restriction of a character to unipotent orbit is given by explicit formula. The breakthrough in the understanding of reducible representation of group G over finite fields for other reductive groups came in 1971 when Tony Springer conjectured a formula chi for character of generic reducible representation of these groups. Using the Brouwer induction theory and the finite field analog Kirillov theory of representations of real unipotent group, I proved, for fields of large characteristic, that Springer's formula for character is a linear combination of characters of representation group with integral coefficient. On the other hand, I have shown that integral of square of character is equal to order of the group. Therefore, the inequality that value of chi at identity is positive allows to conclude that chi is a character of a reducible representation. Green's formulas and Springer conjecture suggest the existence of complexes of Weyl sheaf on G such that functions on the group induced by trace of Frobenius are characters of reducible representation. This expectation is almost correct. The theory of character shift developed in mid-80s by Lustig provides a correction and leads to a description of characters of all reductive groups over finite field. Now the new topic. In 60s, Verma defined a category O of representation of complex reductive groups and constructed special objects called Verma models in this category parameterized by positive weights of Lie algebra G. In the paper of Berninsen, Gelfand, they realized the importance of understanding of the structure of a category for a theory representation of real reductor groups, and in a series of papers developed the study of category O. In particular, we proved the following important result. First of all, the Verma model has a unique reducible quotient, and these quotients provide all reducible representation of a category O. So fix now regular weight lambda and denote by V, W, LW the classes of Verma and reducible model in Kant theory. The previous statement implied the existence possibility to write the character of V lambda as combination of L mu with non-negative coefficient. My next work, joined work with Lustig, is on combinatorial formulas for these coefficients and the interpretation of these numbers in terms of algebraic geometry. Let W be the Weyl group, be this variety of Borel subgroups, and XW the closure Schubel cell. In late 60s, we conjecture a combinatorial formula for CW and also interpretation. W is dimension of cohomology of stacks of intersection homology shapes on XW. The concept developed at that time by Goretsky, McPherson, and Deligne. We proved that algebraic geometric interpretation implies the validity of combinatorial formula. The interpretation of multiplicity in terms of intersection homology shapes were proved almost immediately by Brzezinski, Kochevara, and Berninsen. The proof based on theory of D models developed by Kochevara and Berninsen transformed the theory of D models in one of the main tools in the theory of representation of real groups. On the other hand, the theory of intersection homology shifts in the hands of Lustig led a description of character of finite groups. The next topic, let F be a local non-Archimedean group, I the Evahori subgroup, and H the affine Hecke algebra. Borel proved the category of representation of group G generated by I-invariant vectors is equivalent to category of representation of algebra H. In the mid-80s, with Lustig, described the algebra H and its irreducible representation in terms of geometry of Springer figures. Yes, and with nilpotent cone, and the complex variety of triples. And the group G hat, X naturally on X, G tilde invariant K theory, has a natural algebra structure. We constructed isomorphism with the algebra H in K theory, equivariant K theory of X, and used isomorphism for description of reducible representation of H. Algebras H and K theory of X are decodification of monoidal categories. Roman Bezrukavnikov lifted our isomorphism to an equivalence. Then the equivalence provides an important example of a local geometric Langlands conjecture. Robert Langlands developed theory of a new topic. Robert Langlands developed theory of endoscopy, which Arthur used in his description of the morphic form for classical groups in terms of the morphic form of GLN. One of the main tools in this description is the fundamental lemma. In our works to Lustig, we originate in the study of affine Springer fibers and outline the relevance of this theory for the proof of fundamental lemma. The affine Springer theory we used by Go in the proof of fundamental lemma. Later, in their work with Fier and Warshawski, we used the affine Springer theory for a definition of perverse T-structure on infinity categorically on a LG equivariant shifts on the loop Lie algebra and for definition of affine character shifts. Let G be a new topic. Let G be a simply laced complex in algebra. H the Coxeter number of G, and G hat the corresponding affine cosmology algebra. We denote by C kappa the category of representation with central charge kappa minus H of finite length, whose quotients are simple highest weight models. Let D be Mondoi, on the other hand, be Mondoidal category of finite dimensional representation of quantum group. In serious work with Lustig, we establish equivalence between category C kappa in dq when q is exponential or minus of IP over kappa. To achieve this goal, we first define the Braden-Monoidal structure on the category C kappa and use this structure for a construction of equivalence. Later, Misha Finkelberg deduced from our result a variant equivalence for positive kappa. A new topic. The Satake isomorphism is one of the basic tools in the theory of representation of reductive group over finite fields. In our works with Braverman, we outline an analogous theory for affine cosmology over non-Archimedean local field. In particular, we prove a generalization of Satake isomorphism to the affine case, relating representation of double affine algebras to integral representation of a Langlands dual affine cosmology group. We also develop and join the work of Patniak, a theory of Ahori-Hecke algebras associated to these same groups. The resulting algebra is shown to be closely related to Cherenik double affine Hecke algebra. Furthermore, using this result, we give an explicit description of affine Satake isomorphism, generalizing Macdonald formulas for spherical function in finite dimensional case. Recently, I became involved in two different ways of an extension of Langlands program. One is on the codification of Langlands correspondence, and second, on the extension of this correspondence to the case of curves over local fields. In a series of papers with a number of people, we introduced and studied the category of automorphic shifts with nilpotent support on the stack of principal G bundles on a curve over finite field. In particular, we have shown that the trace of Frobenius and the factor is isomorphic to the space and ramified automorphic function on the points over a stack over finite field. The last topic. The Langlands program for a curve over finite field studies in the unramified case the joint spectrum commuting Hecke operators acting on a space of L2 functions of groupoid of Q points of a stack of G bundles on X. The Langlands conjecture represses the spectrum in terms of Galois data associated with homomorphism of phi1 in the Langlands dual group. In the recent work with Ettinghoff and Frenkel, we study analog of this problem when finite field is replaced by local field. We define analogs of Hecke operators on a dense subspace or Hilbert space of densities on the point of a stack over a local field and prove that at least in some interesting cases that these operators extend to commuting compact normal operators. Our compactness conjecture suggests the same result holds for all reductive groups. The study of Hecke operators for curve over a local field is a hybrid of algebra and functional analysis. In the case of a complex field, Hecke operators commute with global holomorphic differential operators as well as their complex conjugates. This enables the parameterization subject to compactness conjecture of a joint spectrum of Hecke operators for operas corresponding to dual group with real monodromy. These operas play the role of Galois data appearing in the case of Langlands correspondence for finite field. So our description of the spectrum of Hecke operators over C in the operas is an analog of Langlands correspondence in the case of complex curves.
Thank Professor Kastang for the wonderful talk on the Now is the time for the Q&A session. And so it's a chance that to ask the two great mathematicians about mathematics, about the life of mathematicians, and any other questions. Please type your question in the Q&A button, and any question from the high school students, undergraduate, graduate students, colleagues, and the general audiences are very welcome. So since it actually takes the time for the participants to type in questions, so may I take the chance to ask Sasha and David the first question? I've seen that there are many student participants for today's lecture. So do you have any suggestions to the students who just enter into the field of representation theory and actually wants to study? Do you have some advice for them? Hello, yes. Please unmute yourself, Sasha and David.
Yeah, I think I'm on mute. Do you hear me?
Yes, I hear you. Yeah.
Okay. So the kind of hard to give such a general advice, but I think it's one of the main things. I give two advices. One is not to be in a hurry, but to try to understand very well the concepts of which you learn. The second is to have a group of friends with whom you together discuss interesting questions.
Well, maybe for I would join to David's advices, but maybe mine would be to find a topic which is somehow connected with your with your inner world. Mathematics is huge, but it's very important to do things which are truly important to you, and it takes time to find them.
Okay, thank you very much. And now I have seen some questions from the audience. So one question is that, so as far as I know, geometrical long lines is not proved. Do you suspect how we are going to prove it?
First of all, there are interesting cases in essentially for GLN, geometric lengths is essentially proved. There is a lot of advances in recent years. It looks like quite possible that it will be proved in the near future, but it's hard to make predictions.
Well, I agree with David. Also, well, it's difficult to tell how it would be proved, but really the progress is quite great, and one can hope that soon the different threads would converge to solution.
Okay, thank you. And the next question is, zeta function can be defined for projective varieties. If possible, there is some difference from affine variety. So this is a question actually from C1, probably a student.
Well, zeta function can be defined for any arithmetic variety, but those for smooth projective varieties, they have especially nice, should have especially nice properties like a functional equation and others. And zeta functions of affine varieties are actually studied using well, they can be expressed as some products of zeta functions or L functions of projective varieties.
Okay, so well, the next question, and well, actually, it's not a question; it's a request. And so maybe actually, I read actually all he or she typed. So, dear Professor Berninsen and Professor Kastang, thank you for your nice talks. I myself study representations of linear algebraic groups, so I know many terms mentioned by Professor Kastang. May I request for the slides of your talk, Professor Kastang? So I think that the video will be online later.
Yeah.
Yes. Okay, so the next question is for Professor Berninsen. Since you have done research on the topics of Riemann zeta function, what are your thoughts on the Riemann hypothesis?
Well, I do not have special insights, particularly for Riemann hypothesis. It's, well, it's, well, anyway, the things are difficult and beautiful. I do not have something to say in one phrase. Maybe that people, well, there was a great success for proving analogs of Riemann's hypothesis for varieties over finite field due to Grothendieck and Deligne. And but it comes because geometry over finite field is very much better behaves. For example, you cannot in the current mathematical world the notion of a square of spectrum of integers makes no sense, and therefore all geometric proofs do not extend
in any sense to number theoretic situation. But there are lots of attempts to try to invent something in this direction, which are, but it's not a geometry in common sense. It's much more rather a sort of probabilistic geometry. Well, and I have no idea of whether it would lead to proof of Riemann's hypothesis, but these topics are extremely interesting and wonderful.
Thank you. Well, since we are still waiting for the participants to type in questions, and so maybe actually let me actually ask another question for both Sasha and David. Well, in a talk, I mean, in both of the talks, actually, you actually mentioned actually the beautiful connection between the geometry and the representation theory. And well, so actually, if you actually look, I mean, nowadays, I mean, it's actually, I mean, everybody actually talk about the geometrical representation theory, but actually, let's say actually back to the 1970s, and when actually this area was first developed. So actually, how do you actually come up with this idea of combining geometry with representation theory?
For me, the first work, as I was saying, was work of Green. He have shown the different series of representation of GLN are really come together through traces of representation of the Weil group. On the other hand, as Grothendieck explained to us, by that time, way traces of appear very naturally in the action of cohomology. So it became very natural to expect there is some cohomological interpretation of characters of representation of the group. For me, this was kind of the first glimpse of the geometric existence of geometry. In addition, there were works of Bert Constant in theory of representations in the late 50s, unrelated to characters, but he was using algebraic geometry and obtained very powerful results in representation theory as a result using the tools of algebraic geometry. This was another hint for me.
For me, maybe it was one work was the work of Kemp, where my models were interpreted as spaces of local cohomology, and this looked very much similar to standard models, and well, what else do I remember? Well, when I entered the thing, there were also already the works of Kastang and Lustig, where essentially all my ideas, connection with the model theory, were already developed. So.
Well, I'm not sure if there's some connection problems with Professor Berninsen.
I hear you well.
So maybe actually let's wait a little while to see if Professor Berninsen reconnects. Okay, so maybe in the meanwhile, and since we are still waiting for Professor Berninsen to reconnect, maybe actually let me actually take this chance to ask Professor Kastang another question. And well, so we just talk about the history, and I've seen that you have actually done a lot of the great works. So maybe actually now we actually have a question about the future. So can you actually list some of the major open problems in this area, so that actually the students they might be interested in, and they might be able to actually study and maybe even try to solve it.
All right. I see two open areas. One is usage of geometric kind of London theory for number fields. Some of this is done starting from work of Taylor and on, but it's not yet developed in the same way in which is developed in the case of fields of finite characteristics. So the first question, area I see. The second area is the relation with physics. There is works of Witten and Kapustin and many works afterwards, which show that geometric Langlands correspondence, not number theoretical Langlands, geometric Langlands correspondence somehow fits very well to study of four-dimensional gauge theory or string theories and different attempts at the relation physics. And I expect that this direction brings together intuitions from physics, quantum field theory, string theory on one hand, and algebraic geometry on the other hand, will really bring a completely new developments. So I would outline these two areas as kind of main direction for the future, which I foresee. Life could be completely different.
Okay, thank you very much. And also, may I actually ask you more? Okay, so Professor Berninsen is coming back. So we just actually talk about actually the possible future open areas that actually probably suitable for the students. And so Professor Kastang just actually mentioned actually one possible is just the connection with physics. Well, well, as far as I know that, well, many students in China and also including the Hong Kong area, when they actually when they like in the math department, they actually did not study much of the physics. And so, do you actually have any specific suggestions about actually how the student in the math department may learn some of the physics, which actually might be actually helpful for their future research?
The problem is that it is in itself a very large area, and it's almost impossible to combine both of them. So what I would suggest is for people who study mathematics to have interest in physics, to look in this direction, not so much as taking formal classes, but to try to understand basic concepts and try to see why there are some unexpected interactions between physics and mathematics. Let me give you a completely stupid example from ancient times. You have mathematical problem, you have triangle, and you want to prove that medians intersect in one point. And you can prove it. It's kind of elementary school mathematics. On the other hand, if you are a physicist, you put masses in the vertex of triangle and you compute the center of mass. There are three different ways to compute center of mass. You first compute center of mass of one pair of points and then the other. And you find a proof of mathematical theorem which requires some kind of arguments to become absolutely obvious if you think in terms of physics. What is the difference? The difference is that physics has intuition about existence of center of mass, which is not a part of elementary geometry. So what really comes to mathematics, from physics to mathematics, is not so much formal reasoning as new ways, new kinds of intuition. So one should be attuned to possibility of these very important intuitions.
Well, I'm more than agree, and the problem is that somehow mathematical studies, they in a sense they prevent you seeing this physical intuition. And like even in example of David, and the important thing, well, is to try to open your mind to this new intuition, and this is difficult if you are already a professional. So it's better to do it while you are a student.
Okay, so thank both David and Sasha for the valuable suggestions. And now I see there's actually another question coming from the audience. What is geometric about geometrical representation theory? Is it that the group studied are geometrical objects, or that some other geometrical objects arise naturally?
There is no contradiction. Of course, the star group as geometrical objects, but many other geometrical objects appear. For example, in the case of when D models appear, there was the flag varieties in some kind of, for the case of SL2, just projective line, but in general group, flag varieties. And geometry of these flag varieties, they allowed details of geometry of the flag variety, produced interpretation of, produced answer to questions which formulated in representation theory. As I was saying in my lecture, we have coefficients of relating Verma model and reducible models. These coefficients are positive coefficients, which actually dimensions of some homology group related to the structure of a Schubert cells on a flag variety.
Yes. Well, probably I have nothing to add to what David told.
Okay, so maybe this actually related to the last question, and well, so let's actually talk about the Casanova conjectures. I mean, so the proof is actually geometric by Berninsen, and Belinsky Kashiwara, but actually so recently there is actually another approach by Elias and Williamson view the Zogo by modules, and so in this case they actually handle many Coxeter groups where they actually does not arise from geometry. So I mean, is this actually you should think about this actually as some kind of the hidden geometry, or this, or is just there's no geometric objects would eventually involve.
I think a good analogy, if you consider to vector space, when people start doing representations, they can say representation of functions on vector spaces. But later, they obtain representation in vector spaces which are not realized as functions. One can say the geometry used in proof conjectures Lustig was really based on ability to deal with category of, say, perverse sheaves on varieties. What Williamson and other people show that you really, it's actually Sorgel started, but that you can define analogous categories even in the case where there's no geometry. In the same way as the vector spaces, which not realized nature is space of functions, there are categories relevant for representational groups which don't come as category of shifts on a variety, become different. It is still very few cases when it is so. One can expect that it will be developed more. Majority of cases, when I know application to group representation, really uses. So essentially, what Serger and Williamson have done, they extended not only solution, but also questions. We started with representation of a group over finite field. These groups don't exist.
But Hecke algebra could be extended to the case with no group, but it is slightly different direction.
Maybe I would give just another example, which is not exactly this, but very much connected. You can answer various questions about geometry of polytopes using right geometry. If you have a polytope, there are toric varieties connected with this, and then you can use. And there are various important conjectures in combinatorics that were proved in this manner for polytopes. Which are rational, with vertices in having rational coordinates, but not all convex polytopes come in this manner. And then at some point, and for other polytopes, you just do not have such an interpretation. But somehow the methods were pushed through by various mathematicians, Loons, for example, and they proved the corresponding conjectures in full generality. And that's a little bit similar with Williamson's work.
Okay, thank you very much. And now there's another question. Hi, Professor David Kastang and Professor Alexander Berninsen. In your lectures, you mentioned the series of infinite category. I noticed that this abstract theory is widely used nowadays, such as in representation theory, motific geometry, or derived algebraic geometry. So why the infinite category is important in modern mathematics? Is it necessary for young researchers to learn this language?
I think that for people who work in the area of representation theory, it's very important. The question is essentially infinite categories. The structure comes when you want to consider equivalence relation. If you have said, if you have an equivalence relation, you of course consider new set of equivalence classes. But in this case, you forget about the way you identify points. If you want to remember more, not only the set of equivalence classes, but if you want to remember how they become equivalent, and you think it through, this essentially leads you to theory of infinity categories. So I think it is important in many areas when equivalence relations are important. They're definitely important in topology. The homotopy topology, important in the representation theory. But I expect it to be important in many other cases because it expresses a way not to forget the way you took to identify objects.
Maybe to add it is that in older days when infinity categories did not exist, well, typical things that people worked with were derived categories, usual derived categories, triangulated categories. But the thing is, or in topology, just theory of just plain homotopy types. But the thing is that in this world, there is absolutely no way to make any constructions that passing from just two rigid category of complexes to derived category, you lose any ability to construct objects. infinity category is somehow a way to live in the world where constructions are still possible. This world is in between two rigid things like plane logical spaces, plane complexes, and objects like homotopy types or objects of derived category with which the constructions are impossible. And well, it's still a complication of constructions of definitions of infinity category is that we still work in the world of rigid objects, except we understand well how to go to something less rich. We just do not have some strange enough, but in our intuition working with infinity category, it should be in principle that infinity category should be our basic objects of intuition. But it's not at the moment, and for this reason the subject is not immediate and not complicated. So there is something deep that is not understood on the level of intuition. I will just mention.
Okay, thank you very much. And so maybe let's actually have the ask the last question. So it's from Bin Xu. Professor Berninsen and Professor Kastang, do you think if there exists a localization theorem for representations of p-adic groups, as in the case of real groups?
The question depends on way to understand word localization. If you understand localization and the existence of D models, then the answer must probably no, at least if you do consider p-adic representation of p-adic groups. On the other hand, if you understand localization and essential use of algebraic geometry, which in a kind of complex case based on the modus, then I do believe that it will be essentially very similar, but structured differently, a way to use algebraic geometry of corresponding varieties. This theory does not yet exist, but I would not be surprised if it will appear soon.
Well, I agree. I have nothing to add.
Okay, so I'll say let's thank Professor Berninsen and Professor Kastang for both their wonderful talks and for sharing their insights in mathematics. And so this is the end of the Shell Prize lecture. And thanks for joining us.
Thank you very much.
Thank you very much.
Thanks very much.